How many Gs can the human body actually survive? Ask that question and you get two completely different answers, because everything depends on one word: how long. This video works through three real numbers, and the gap between them is the whole story. Start with the number a trained body can hold for seconds at a time, not an instant. Fighter pilots train against roughly 9 Gs, 9 times their own body weight, pressing blood out of the brain and down into the legs. That is why they wear pressurized G-suits, inflatable bladders that squeeze the lower body and fight to keep blood where it is needed. Even with training and equipment, 9 Gs sustained is close to the edge of what a conscious human can manage. Take the suit away and the number collapses. An untrained person, no G-suit, starts losing consciousness somewhere around 4 to 6 Gs. This is GLOC, G-force-induced loss of consciousness, and it happens because the heart simply cannot pump blood uphill against that kind of sustained force. The brain runs out of oxygen in seconds, and the pilot blacks out, sometimes with no warning at all. So, 9 Gs, trained, with equipment, sustained. 4 to 6 Gs, untrained, sustained. Those are the limits your circulatory system sets once the force lasts more than a second or two. Now the third number, and this is where sustained G-force and instant G-force turn out to be almost entirely different problems. On October 12, 2003, IndyCar driver Kenny Brack crashed at Texas Motor Speedway at over 200 miles an hour. His car's onboard crash recording system measured a peak deceleration of 214 Gs. 214. That is roughly 24 times the sustained limit that blacks out a fighter pilot, and Brack was conscious enough afterward to describe the impact. He broke his femur, his sternum, a lumbar vertebra, both ankles. He did not lose consciousness, and he survived. Guinness World Records lists it as the highest G-force a human has endured non-voluntarily. How is that possible? Because GLOC is not caused by force. It is caused by force sustained long enough for your heart to fail to keep up. Brack's 214 Gs lasted a fraction of a second, not long enough for blood to actually drain from his brain, even though it was, for that instant, more than 20 times what would black out a fighter pilot in level flight. This is the same shape this channel keeps finding. The danger was never really about the number on the dial. It is about how long that number holds. 9 Gs for 10 seconds can end a mission. 200 Gs for a tenth of a second can leave you with a broken leg and a story. There is an older data point that makes the same case from the opposite direction. In the 1950s, U.S. Air Force Colonel John Stapp rode rocket sleds at Holloman Air Force Base to measure exactly these limits on himself, deliberately, without a crash. His most extreme run decelerated at 46.2 Gs, sustained across roughly 1 second, not a spike. He survived, temporarily lost vision from burst blood vessels in his eyes, and kept doing it anyway. 46 Gs held for about a second was already at the edge of what a prepared, restrained, forward-facing human body could take on purpose. So the honest answer to how many Gs a human can survive is not one number. It is a curve. 9 Gs if you can hold it for a while. 46 Gs if it is over in about a second. 214 Gs if it is over in a fraction of that. No number here is invented. Where the real ceiling of that curve actually sits, the true instantaneous limit, nobody has measured, because nobody has designed the experiment. How much warning would we actually get before a city-killer asteroid hit? Not the movie version, where a telescope spots it years out and a crew of heroes gets launched in time. The real version, built from the actual capabilities of the systems watching the sky right now. 2 numbers. The gap between them is the entire problem. Start with detection. A city killer in this conversation means something in the range of roughly 140 meters across, big enough to level a metropolitan area on impact, small enough to be genuinely hard to find. Objects that size don't glow. They don't announce themselves. They're dark rock, reflecting a small amount of sunlight, moving against a background of 100 billion stars. Current survey systems, like the Atlas network of telescopes, are built specifically to catch these before they arrive. For an undiscovered object around 140 meters wide, with an impact energy around 100 megatons, Atlas can provide as little as 3 weeks of warning. A 50-meter object, still capable of leveling a city center, might only be caught about a week out. 3 weeks. That's the detection side of the equation, for an object nobody has spotted yet. Now the response side. The only planetary defense method that has actually been tested, not modeled, not proposed, tested, is the kinetic impactor. Slam a spacecraft into the asteroid at high speed and nudge its orbit just enough to miss Earth. NASA's DART mission proved this works in September 2022, successfully shifting the orbit of the asteroid Dimorphos. But look at the timeline. DART took 5 years from mission start to impact, and that was a controlled test against a known, well-characterized target, with no crisis pressure and no need to build the spacecraft from scratch under emergency conditions. Planetary defense researchers are consistently clear that a real deflection campaign needs years to decades of lead time to reliably work. 3 weeks of detection, in the worst case, for an object nobody has found yet. Years to decades needed to actually do something about it. That's not a small shortfall. That is potentially the entire warning window, gone, before the response can even begin. To be clear about what this isn't, for a large asteroid that's already been found and catalogued, we typically get decades of warning, because its orbit is known and tracked. The 3-week number describes the genuinely dangerous case, a mid-sized object that has never been spotted before, approaching from a blind spot, like out of the sun's glare. That is the scenario where detection and response are on a collision course with each other, not just the asteroid. No figure in this video is invented. The 3-week and 5-year numbers both come from real systems and real missions. The gap between them isn't a guess. It's the honest shape. Beneath the border of Switzerland and France, there's a ring-shaped tunnel that took a decade to build and now smashes protons together at nearly the speed of light. This video works through 4 real, published numbers about what that tunnel actually cost, and why CERN's next one will dwarf it. Start with the length. The Large Hadron Collider tunnel runs 27 kilometers in a circle, buried roughly 100 meters underground. Particles racing around that ring complete more than 11,000 laps every single second. Now the cost. According to CERN's own reported figures, the machine and tunnel together cost approximately 4.3 billion Swiss francs. That number is specifically for the accelerator infrastructure, the detectors that actually observe what happens when particles collide. Instruments like Atlas and CMS were funded separately, adding roughly 1.5 billion francs on top of that. Divide 4.3 billion francs by 27,000 meters of tunnel, and you get a cost of approximately $180,000 per meter. Per meter. That single number captures just how expensive it is to bore a precision scientific instrument through solid rock, deep enough to shield it from cosmic radiation, straight enough to keep beams of particles on course for 27 kilometers without drifting off target. And here's why that number matters right now. CERN has proposed a successor, the Future Circular Collider. Its first phase would be 91 kilometers around, more than 3 times the length of the LHC's tunnel. According to CERN's own feasibility study, that first phase is projected to cost approximately 15.3 billion Swiss francs, somewhere around 17.4 billion US dollars. 27 kilometers for 4.3 billion francs. 91 kilometers proposed for 15.3 billion. The tunnel gets 3.4 times longer, but the projected cost only grows by about 3.6 times, a scale that roughly tracks the increase in length, which is itself a real engineering achievement, even before a single new particle gets discovered. No figure in this video is invented. Every number here comes from CERN's own published. $1 trillion gets thrown around constantly: government budgets, market valuations, national debt figures. It's said so often that it stops sounding like a real quantity. So this video is going to make it real, with one simple rule: you get to spend exactly $1 every single second, with no breaks, forever, until the money runs out. Start with the rate. $1 per second. Not a lot, slower than a fast food purchase, slower than a vending machine transaction. At this rate, in 1 minute you've spent $60. In 1 hour, $3,600. Completely unremarkable so far. Now the real number. $1 trillion is 1 followed by 12 zeros, 1 trillion. At $1 per second, spending that entire amount takes exactly 1 trillion seconds. Not a metaphor, direct division, $1 trillion divided by $1 per second equals 1 trillion seconds of continuous spending. Convert that into something you can actually picture. There are about 31,536,000 seconds in a year. Divide 1 trillion seconds by that, and you get approximately 31,709 years. 31,709 years of spending $1 every second, without stopping, without sleeping, without a single pause, and you still wouldn't be done. For context, all of recorded human history, writing, cities, empires, everything we have documentation for, spans roughly 5,000 years. Our $1 per second spending spree would need to run more than 6 times longer than that entire span just to get through a single $1 trillion. $1 per second. 1 trillion seconds to spend $1 trillion. 31,709 years. 6 times all of recorded history. No figure in this video is invented, it's arithmetic, run out loud, on a number too large. What actually happens to matter 6,000 meters below the ocean surface? Not in theory. In actual, measured atmospheres of pressure, pressing on an actual, measured area. This video works through 3 real numbers, and by the end you will understand why almost the entire ocean floor is a place no unprotected human body has ever touched. Start with the baseline everyone already lives inside. At sea level, the air above you presses down at 1 atmosphere. You don't feel it, because your body evolved inside it. Water is roughly 800 times denser than air, so pressure builds fast as you descend, about 1 additional atmosphere for every 10 meters of seawater. Go down 100 meters, and you're already at 11 atmospheres. Go down 6,000 meters, and the number reaches roughly 600 atmospheres. 600 atmospheres. That's the first number, and on its own it's just a figure on a gauge. So let's turn it into something your body actually understands. Take an area about the size of a human palm, roughly 100 square centimeters. At 600 atmospheres, the force pressing down on that single palm-sized patch works out to approximately 62 tons. 62 tons, on an area you could cover with one hand. That's heavier than a fully loaded semi-truck, concentrated on a patch of skin. There is no version of unprotected human tissue that survives contact with that number. This isn't a slow injury. It's instantaneous. So how does anyone actually reach those depths and come back? Not by resisting the pressure. By building something rigid enough to hold a bubble of 1 atmosphere air inside an ocean trying to collapse it from every direction, evenly, all at once. The real engineering answer is the third number. The DSV limiting factor, a real, currently operating full ocean depth submersible, uses a pressure hull 9 centimeters thick, machined from titanium into a near-perfect sphere, accurate to within a fraction of 1% of true spherical form. That precision matters. A sphere spreads crushing force evenly across its entire surface. Any flaw, any deviation from that shape, becomes a weak point the ocean will find. This is the same vehicle class that has carried pilots to the deepest known point in the ocean and back, repeatedly, on a titanium shell less than the width of your hand. Put the 3 numbers together and the shape of the problem is the same one this channel keeps returning to. 600 atmospheres is the environment. 62 tons on a palm is what that environment does to anything unprotected. 9 centimeters of titanium, shaped to a near-perfect sphere, is the entire margin between the two. No figure in this video is invented. Where the exact numbers vary by source, we use the most directly measured and documented ones available. The ocean below 6,000 meters isn't dangerous because it's mysterious. It's dangerous because the arithmetic is completely unforgiving.